Okay, welcome back. So in the first part of this videos on the kinetic theory of gases, I explained to you about what is meant by the kinetic theory of gases and various properties of matter and how the kinetic theory of gases can be explained using the assumptions. Now finally I explained to you about the relationship between the pressure and the velocity or the momentum of a gas. Now I'll begin with the same concept here. Now pressure, I am using the pressure to explain about this concept because I need to explain you about the mean square of the speed, which is the basis of this video. And also in this video I'll be talking about the explanation of the gas laws, the basic gas laws using the kinetic theory of gases. Alright, to begin all these concepts, I'll derive a relationship between the pressure and the mean square of the speed. Now I'll explain about the mean square of the speed here. First of all, alright, so the mean speed of a gas is that, now say if you have a gas sample of molecules traveling at velocity of actual speed at speed of 2, 4 and 6 in some direction, you can say that the mean speed of a gas, of that gas, is actually the average of the speeds of the individual molecules. Now if you have, for example, as I mentioned, velocity speeds of 2, 4 and 6, the mean speed of that gas sample is 2 plus 4 plus 6 over 3, because there are 3 molecules. So we take the summation and we divide it by the number of molecules. So in this case it is 2 for the first molecule, 4 for the second molecule and 6 for the third molecule, and it should be divided by 3 since there are 3 molecules. So that will be 2 plus 4 is 6, 6 plus 6 is 12, 12 by 3 is 4. So the mean speed of this gas is 4. Now in the case of velocity, now you know that the total velocity of this object should be 0, right? Because now if some molecule is moving in some direction with some speed, another molecule will cancel out that velocity with a higher speed or a lower speed. So finally what actually happens for the whole gas sample is that the total velocity of the molecules is 0. Since the total velocity of the molecules is 0, the mean, if you define a mean velocity for that molecules, you can say that the mean velocity, as in the case of mean speed, is that the total velocity divided by the number of molecules. Since the number of molecules, although the number of molecules is not 0, the total velocity of the molecules is 0 for any gas, so the total or the mean velocity of that gas is 0. So it's practically useless to define the mean velocity of a gas. So we do not define the mean velocity of a gas, we only define the mean speed of a gas. However, you know that although the pluses and the minuses cancel out, and this makes the algebraic sum of the velocities of the gas, of the molecules of a gas, 0, when you square the velocities, even the minus velocities or the negative velocities will have positive values. So when we square the velocities, we don't have to take the direction, we only have to take the magnitude. So when you square the velocities, when you take the algebraic sum of that square of the velocity, now for example, if you take the same gas sample in which we have 3 molecules of speeds, actually velocities 2, 4 and 6 in some direction, now these 2, 4 and 6 may cancel out each other. Now 2 and 4 is 6, and those 2 molecules will be traveling in some direction, and that the third molecule, which is traveling with a velocity of 6 meters per second, will be traveling in the other direction. So the total velocity is 0. But if you square this, 2 squared plus 4 squared plus 6 squared is never 0, right? Because 2 is a real number, 4 is a real number and 6 is a real number. You know that when you square the real numbers you get positive values, when you add some positive values you never get 0, right? So the total square of the velocities, total sum of the square of the velocities is never 0. So we define not the mean speed, the mean velocity of a gas, but the mean square speed or the mean square velocity of a gas. So mean square speed or the mean square velocity of a gas is the algebraic sum of the total velocity of the molecules inside a gas divided by the number of molecules. So this is actually the same thing we learned here. The only difference is that now we don't add the total velocities here. right? We don't add the velocities here, we square them and then add and then take the mean, right? We also define the root mean square of the speed. So the root mean square is taking the square root of both these sides. So root mean square will be important in the concept that I'll be explaining you in the latter part of this video. So remember that the root mean square of the speed is the square root of the mean square speed or the mean square velocity. So the mean square velocity is the algebraic sum divided by the number of molecules. We take the square root and we find the root mean square. Now if you calculate, for example, we will take a practical example. Now we take 3 molecules, those 3 molecules, 2, 4 and 6. You know that when you take the speed, that the mean speed is 2 plus 4 plus 6 divided by 3 is 4. If you take the mean square speed, that will be 2 squared plus 4 squared plus 6 squared divided by 3. So 2 squared is 4, 4 squared is 16, so 4 plus 16 is 20, 6 squared is 36, so 20 plus 36 is 56, and that 56 divided by the number of molecules, which is 3, will be 56 over 3, or will be approximately 18.66, right? And when you take the root of that, the root of 18.66 will be somewhere between 4 and 5. Now you know that the velocity here is actually the mean speed. Mean speed is 4. The square root of the mean speed is 4 point something, and that the mean speed is greater than the mean square speed, root mean square speed in fact. However, both these are 4 or close to 5, those values. However, this value we got 18.66. So we can say that we can note that for any gas, whether it has 2, 4, 6 or infinite number of molecules with various magnitudes for the speed and the velocities, we can say that C bar or the mean speed of the molecules is only a little smaller than, or the root mean square speed is little greater than the mean speed, but both these factors or both these magnitudes are far smaller than the mean square speed or the mean square velocity. So I explained about the mean square speed and the mean square velocity to explain you about the relationship between the pressure and the mean square of the speed. Now there exists a relationship between the pressure of a gas and the mean square velocity, and the pressure of a gas in fact depends upon the mean square speed of the gas. So this is due to two facts. One fact is that the momentum change on a wall. Now what I mean by a wall is actually the wall of the container in which the gas is contained, right? In which the gas is stored, is proportional to the speed. Now you know that because the mass of a gas doesn't change when you increase the temperature of a system, right? You can say that the velocity increases but the mass doesn't increase, so the momentum should be proportional to the speed, right? So that's obvious even from the actually the basic concepts of mechanics. And the second thing I have to mention here, that is the number of impacts per second at a given surface is proportional to the speed. So I explained about this in detail in the first video on the kinetic theory of gases. When the speed increases, you know that the speed is the distance, the rate of change of distance, or the distance per unit time. So when you take a unit time, speed is proportional to the distance. When you increase the speed by somehow, for example by increasing the temperature of the system, you can increase the speed. So when you increase the speed, the distance moved per unit time increases. So if you take two gas samples in which we have a speed of 2 meters per second, a molecule, I will take a simple molecule, a single and a simple molecule. In the first sample, I have a molecule which is moving at 2 meters per second, and in the second sample, I have a molecule which is traveling at 4 meters per second. So the distance moved within a second of the molecule in the first sample is 2 meters, and that of the second sample is 4 meters. So it takes only a small time for the molecule in the first sample to reach the other wall, right? So if you have 3 or 4 molecules which are moving in a similar vein, we can say that since when the speed is high, the molecules reach the other wall in a very less time. You can say that when you increase the speed, the number of impacts per second should be probability. According to the probability, you can say that the number of impacts per second is high. So when the number of impacts per second is high, as I explained in the first video on the kinetic theory of gases, the force exerted by these molecules on the wall is high. So pressure is defined as the force per unit area. So if you take the area to be constant, it should be the constant, right? Area of the container in which the gas is contained is a constant. So the pressure is proportional to the force is proportional to the speed. So finally pressure is proportional to the number of impacts and the speed. So the rate of change is proportional to the square of the velocity. Thus the pressure, which depends on the rate of change of momentum, is also proportional to the square of the speed. So that's the relationship between the pressure and the momentum, pressure and the square of the speed, which I couldn't explain in the last video. So I'll come to the second part of this video, and I'll explain now about the explanation of gas laws used in the kinetic molecular theory of gases. Alright, so in the first part of the video, when I classified the matter into two types based on the method of inspection as microscopic properties and the macroscopic properties, I explained to you that the macroscopic properties are explained by the microscopic properties. So here I will use that theory that I explained to you about the relationship between the macroscopic properties and the microscopic properties to explain the gas laws using the kinetic molecular theory of gases, or the KTG. So the first explanation will be between the kinetic theory and the Boyle's law. So when explaining about the kinetic theory, the relationship between the kinetic theory and the Boyle's law, I can say that the pressure of a gas is the force exerted on the walls, and these are due to the collisions between the molecules and the wall, right? So if you consider a container with a movable piston, right, fixed to one wall, you can say that when the piston is pulled to make the volume actually half or one third, you can say if you keep the temperature of the system constant, if the temperature is constant, you can say the mean kinetic energy of molecules is a constant. So when the mean kinetic energy is a constant, these molecules travel in a very fast way, and the number of molecules in a unit volume is also doubled by halving the volume. So due to these reasons, what actually happens is that halving the volume increases the pressure, because there are when you decrease the volume by some extent, you can say that the number of collisions at some wall increases. So since the number of collisions is directly proportional to the pressure, when the volume is decreased, or when the volume is halved, you can say that the pressure is doubled. So this is about the Boyle's law, inverse relationship between the pressure and the volume. The second relationship is between the kinetic theory and the Charles law. Now, according to the kinetic theory, we can say that when the absolute temperature, right, temperature is increased, the mean kinetic energy of molecules increases. So, you know that I explained to you in the last video when I explained about the introduction to kinetic theory of gases. So, when the number of collisions increases, what happens is that when the kinetic energy increases, the velocity of the molecules increases, thus it takes less time for the molecules to move from one place to another. Thus the probability of the number of molecules taking place increases, number of collisions that take place increases. When the number of collisions increases, you can say that the pressure of the gas should also increase. However, as in contrast to the theory that I explained a little while ago about the relationship between the kinetic theory and Boyle's law, if you keep the pressure constant now, the volume of the gas should increase. So that's obvious from a practical concept. So since the volume of the gas increases, you can say that there's a direct proportionality between the volume of a gas and the absolute temperature when the pressure is kept constant. So this is about the Charles law. So the third relationship is between the kinetic theory and the pressure temperature law, also called the Charles Gay-Lussac law. So you can say in a similar way that if you keep the volume constant, as I explained in the case of Charles law and Boyle's law, you can say that if you keep the volume constant, the pressure should be directly proportional to the absolute temperature, because when you increase the temperature, the number of collisions increases, so the force exerted on a particular wall increases. So finally, you can say that when the absolute temperature increases, the pressure of this gas should increase. So there is a direct proportionality between the pressure and the temperature. Finally, you can also explain the kinetic theory, relationship between the kinetic theory and the Dalton's law of partial pressures. Now, consider that when a new gas is introduced to an existing gas sample at some constant temperature and volume, the number of molecules in a unit volume temperature increases. So the number of collisions increases and the pressure increases. So that's actually about the final explanation about the Charles Gay-Lussac law, or that the pressure is directly proportional to the absolute temperature. When these two gases do not mix with each other and they behave independently, the total pressure of the gas sample is the sum of the partial pressures exerted on the sample by the two gases. So if you take two gas samples, you have some pressure from the first gas, you have some other pressure from the second gas. So it's obvious that the total pressure should be the summation of these partial pressures. So that is about the Dalton's law of partial pressures. So that is about the explanation of the gas laws using the kinetic molecular theory of gases. So as the last part of this video, I'm going to build up a relationship for the kinetic molecular theory of gases. So this is actually a standard and a common relationship. Now you know about relationships that you have already studied under gas laws. So building up a relationship for the kinetic molecular theory is important due to several reasons. One of the reasons for its importance is that now the kinetic molecular theory, you have to consider the base of the kinetic molecular theory. So what is the kinetic molecular theory? As I explained in the first video of the videos on the kinetic molecular theory, the kinetic molecular theory is actually like an interface or a bridge between the macroscopic and the microscopic properties, and hence is used mainly for the explanation of the behavior and the changes that take place in gases when considering the gas laws. So by building up a relationship between the physical quantities that you may come across when solving gas laws, you can easily construct some sort of an equation and then see as to how these a new equation in fact, and see as to how this equation is important when considering the behavior of gases. Alright, so first of all what I'll do is that as in the case of the ideal gas law, PV equals nRT, which I mentioned in one of my previous videos on gas laws, I'll build up a relationship between the pressure, the volume and the other physical factors. So first of all, you know that I have been talking about the pressure throughout my videos on gas laws and my last video on the introduction to kinetic molecular theory and this video as well. So first of all what I'll say is that the pressure is equal to force by area. So you know that force per unit area, and the force is equal to mass into acceleration, and the acceleration is equal to velocity change over time. So finally I can say that the pressure is equal to mass times the acceleration, which is the velocity over time. So that is the force, and that divided by the area. So you can see that from this derivation that the pressure of a gas is directly proportional to the mass of the gas, right? So if the velocity change per time or the acceleration of the particles is a constant, and area of the container in which the gas is contained is normally a constant, so the pressure is directly proportional to the mass, and also it is also directly proportional to the velocity, right? It is also directly proportional to the velocity change. So, and it is inversely proportional to the area. Similarly, it should be noted that the number of collisions which affect the pressure is directly proportional to the number of molecules. Now when the number of molecules in a given unit volume actually decreases, there is enough space for the other molecules to travel and collide with the walls and make impacts and make some forces and then create the pressure. However, when the number of molecules, right? However, when the number of molecules decreases, in fact it's increasing, right? When the number of molecules increases, the number of collision increases. When the number of molecules decreases, what happens is that there is less probability that these molecules will get some sort of a force, will exert some sort of force, and hence some pressure. And it is however inversely proportional to the volume of the container. Now when you keep the number of molecules and the other stuff constant, and when you decrease the volume of the container, what generally happens is that within a unit volume the number of molecules decreases, so there is less space for the molecules to travel, so the number of collisions decreases, right? So you can say that P is directly proportional to nmc squared bar over V. So n is the number of molecules, m is the mass, c squared bar is the square of the speeds or the square of the velocities, divided by V is the volume of the container. So you can remove the direct proportionality by equating it with a constant. So I'll use the constant k. So P is equal to k times nmc over c squared bar over v. So experiments show that k is equal to 1/3, right? You can prove it using some experiments. So that is actually an experimental part. So k is equal to 1/3, that has been proven already. So P is finally nm c squared bar over 3 times v. So we can say that, as in the case of ideal gas law, we can isolate PV term by multiplying both sides by v and saying that PV is now equal to 1 upon 3 mnc squared bar. So this is a new equation built upon the concepts of the actually the kinetic molecular theory of gases. So you know PV equals nRT. So you know now another equation involving PV, which is 1/3 mnc squared bar. So this is a general equation, or the characteristic equation of the kinetic molecular theory of gases. So this can be used in various other derivations. For example, if you consider 1 mole of a certain gas, you can say that the number of molecules is equal to the Avogadro number. Hence you can substitute the Avogadro constant in place of the number of molecules. So PV will be then 1 upon 3 ml c squared bar. However, you know that when the mass is multiplied by the Avogadro number, you know that actually it gets the molar mass, right? So mass times the Avogadro number is the molar mass. So PV equals 1 upon 3 mc squared bar. So we also know that PV equals nRT. So from these two derivations, we can say finally that 1/3 mc squared bar is equal to RT, right? So because we are considering only 1 mole of that gas, so finally c squared bar equals 3RT over m, or c squared bar root is equal to root 3RT over m. So when the temperature is constant for a given gas, the mean square of the speed is inversely proportional to the molar mass of the gas. And also for a gas whose molar mass is constant, you can say that when the temperature increases, the mean square speed increases. So that's another derivation between the temperature and the molar mass, and the c squared bar, which is the mean square speed, and R here is the universal gas constant. So this is all about the kinetic molecular theory of gases. So in the last video, I began with the general introduction of the kinetic molecular theory of gases, and then went on to explain about the assumptions. And in this video, I explained to you as to how the kinetic theory of molecular gases, so the KTG, can be used to prove the gas laws. And finally, I derived out a relationship between the velocity of a gas, the temperature, and the molar mass, and also between PV and mnc squared bar. PV equals 1 upon 3 nmc squared bar, which is the characteristic equation for any gas obeying the kinetic molecular theory. So this is all about the states of matter and gas laws, the first part of the series of videos, and also the kinetic molecular theory of gases. So that covers the total syllabus and the content I expected to cover in the states of matter and gas laws. So see you next time with the introduction of thermochemistry. Thanks for watching all these videos, and see you soon.